thanks for those of you who are staying for my talk. So I'll be talking about a joint work with Professor Walter Strauss on a proof of the modulational instability of Stokes waves in deep water. So I'm thankful to the first talk of Professor Bhakti, who gave detailed descriptions of the water wave problem and in-depth discussions about the existence of water waves that are periodic in space. So Stokes waves are such solution, are such water waves that are periodic in space, but the focus of my talk is not on the existence, but the stability of this class of solutions of the water wave problem. So for an outline of the talk, I'll give an introduction to the problem, and then recall the Zakharov Craig-Sulem formulation, which was already recalled in the talk of Professor Bhakti, and I'll talk about the Stokes waves, the existence of Stokes waves. In the third part, I'm talking about linearization and spectral modulational instability of Stokes waves. Then for the last part, I'll outline the main ideas of the proof. Okay, so as for the introduction, so the theory of water wave has a long history. Started with the work of Laplace in 76, and developed by many other famous mathematicians. So notably, I should mention the monumental work of Stokes in 1847, where he proved this kind of water wave that we call Stokes waves. This is Stokes waves in reality. So they are periodic traveling waves that propagate along a fixed direction. So Stokes found the first exact solutions for the nonlinear water wave problem by means of a formal perturbation series in terms of some small parameters, which is the wave stiffness. By definition, the wave stiffness is the product of the amplitude A and the wave number K. Okay. So let me assume without loss of generality that the wave number K is equal to 1. In other words, the wave has a period 2 pi in space. Okay, and let me denote. So this denote by eta the surface elevation. So this is a typical 2 pi period function, and the surface elevation eta is a function in a moving frame. So x is the variable in the direction that the wave propagates. T is a time variable, and C is the phase speed. So Stokes showed that the surface elevation eta can be expanded into a series like this in terms of the amplitude A, amplitude of the wave. And the method developed by Stokes actually allow one to determine coefficients of all the higher order terms in this series, but it didn't say anything about the conversion of this series. And for a long time, this was a controversy whether or not the series should converge. And more than a century after the work of Stokes, this was independently proved by Nekrasov and Levi-Civita that the Stokes expansion does actually converge to an exact solution to the water wave problem. So with the existence of Stokes waves established, it's remarkable that no one noticed its instability until the work of Benjamin and Feir in 1967, which is more than a century after the work of Stokes. So Benjamin and Feir did an experiment in a wave tank. Here, the top picture shows the Stokes wave near the wave maker, right? The perfect Stokes wave near the wave maker. And in the second picture, it's a Stokes wave at 200 feet farther from the wave maker. So we see clearly that the Stokes waves disintegrate after the traveling far enough. And Benjamin and Feir identified the mechanism of this disintegration as the instability of Stokes waves. So they gave a heuristic explanation of their discovery as follows. Let's assume that the Stokes wave size argument capital X is in the moving frame is x minus ct. And for the disturbance, which is always there, say it's coming from an oscillating pedal, they take a pair of progressive wave modes with sideband frequency and wave numbers, so that the argument of the disturbance modes are given by x1 and x2 like this, where kappa and delta are small parameters, but gamma 1 and gamma 2 don't have to be small. Okay? So let's say the amplitude of the disturbance modes are Aj, which is much smaller than the amplitude of the fundamental Stokes wave. Now, nonlinear interactions of these disturbance modes with the basic wave trend produces new arguments, and among them are 2x minus x1 and 2x minus x2. It turns out that these new arguments are given like this. So if gamma 1 plus gamma 2 tends to some constant as a nonlinear process develops in time, each mode will generate effects that become resonant with the other. And this leads to the growth of perturbations. In other words, the instability of Stokes waves. So furthermore, by assuming certain conditions between the slowly varying functions gamma j, the amplitude aj's, and their derivatives, Benjamin and Feir formally argue that the resonant conditions we just mentioned is achieved in the case of infinite depth. So take the depth equals to infinity. And the case of finite depth were then treated pretty similarly by Benjamin and Witham in the same year. It turns out that the modulational instability is one of the most ubiquitous phenomena in nonlinear science. Just to give you an idea, let's say leading out of vast physics literature must have at least more than 500 papers that mention modulational instability or Benjamin and Feir instability, two terminologies of the same phenomenon. So the work of Benjamin and Feir provided experimental and theoretical evidence of the modulational instability of Stokes waves. However, to make a completely rigorous proof of this instability is another matter, and this is our focus. So it took about 3 decades for such a proof to be found in the case of finite depth. Bridges and Milger in 1995 accomplished the feat by means of a spatial dynamical reduction to a 4-dimensional center manifold within the Hamiltonian framework. And as explicitly stated in the work of Bridges-Milger, their work leaves open the following issues. First, it's a depth go to infinity. At the great depth, the linearized operator of the spatial dynamical system that they consider has a continuous spectrum. And so the hypotheses of the center manifold theory are invalidated. As a consequence, the rigorous proof of the modulational instability for Stokes wave in deep water remains an open problem. The second issue is that the formulation and reduction used in that paper are not readily compatible with energy estimates for the nonlinear problem, and this leads to obstruction in passage from spectral instability to nonlinear instability. And the goal of my talk today is to show you our contributions in this problem. We provide a completely different approach to prove the spectral modulational instability of Stokes waves. Some key features of our approach are, first, it doesn't rely on any abstract theories Hamiltonian system. As a result, it works in both finite and infinite depth cases. So we give a rigorous proof for the instability of Stokes wave in infinite depth. Another feature is that the way we choose the formulations and linearize the problem are compatible with energy estimate for the nonlinear problem, and they retain the physical variables and parameters throughout the proof. So in fact, our approach is inspired by recent works on modulational instability for simplified models of water waves, such as Schrödinger water wave, Schrödinger equations, the work of Gallet-Hieronymus for KV type equations, the work of Hieronymus, Capitula, Pronsky, Johnson himself, also the work of Pearl and Johnson for Witham equation. So to focus only on the main idea of our approach, we shall consider only the unsolved case of infinite depth. And I'm happy to discuss some aspects of the finite depth in case you have comments or questions. So in the second part of the talk, let me recall the Zakharov Craig-Sulem formulations and the Stokes waves. So this is already introduced in the talk of Bekti. We consider the fluid domain of infinite depth below a water surface that is parameterized by some function, say eta of the space variable x and the time variable t. So x is the variable in the direction that the wave propagates. And assuming that the fluid is incompressible, inviscid, and irrotational, the velocity field admits a harmonic potential that I denote by phi. So phi is a function of the horizontal variable, the vertical variable, and time. This is harmonic in the fluid domain. Now, the harmonic potential phi and the surface elevation eta satisfy this water wave system. right? The second equation is the Bernoulli equations, which has two parameters. G is the constant acceleration due to gravity. P is the air pressure up to constant and psi. The third equation is the so-called kinematic boundary conditions. It says that the water surface moves with the fluid. And the last condition is some conditions about infinity. It says that the water is quiescent at great depths. Okay. So this is an Eulerian descriptions of the water wave problem. There's, of course, Lagrangian descriptions, but usually both are not handy for mathematical analysis. And that's why people have come up with various equivalent formulations of the water wave problem. And it is usually the case that to tackle any problem in water wave, choosing the right formulation to work with is already part of the problem. So here we choose to work with the Zakharov Craig-Sulem formulation, which allows to reduce the whole water wave dynamic onto the surface through the introduction of the so-called Dirichlet to Neumann operator, this non-local operator that we denote with the same notations in the work in the talk of Professor Berti. We denote it by G eta because it's associated to the domain with the surface eta. And to define this operator G eta acting on some function f, we first solve the elliptic system for some harmonic function theta that takes the trace f on the surface with some decays at infinity. And then we define the operator acting on an f by this formula, which is precisely the normal derivative and some normalized version of the normal derivative of the harmonic function theta restricted to the surface. Okay. Now with this introduction of this operator, let's denote by psi the trace of the velocity potential at the interface. Then in the moving frame with speed c, the gravity water wave system written in Zakharov Craig-Sulem formulation is this system 5. Right? It has two equations. One is for the surface elevation eta, one is for the trace of the velocity potential psi. And both involve the Dirichlet to Neumann associated to the domain with the surface eta acting on the function of psi. Okay. So by definition, the Stokes waves is a periodic steady solution of the previous system, meaning that the Stokes waves is a pair of two periodic functions, eta and psi, that solve this time-independent problem. And again, for simplicity and without loss of generality, we will talk about 2-pi periodic Stokes waves. So this is to mention again in details the theorem of Nekrasov and Levi-Chivita on the exact existence of Stokes waves. So there's just a family of Stokes waves that are parameterized by two parameters. First is the wave amplitude A, that is small, and second is the air pressure P. Okay, so I would just want to highlight the fact that we can take eta to be even and psi to be odd because this system respects discounted parity. Okay, so, and we call these solution Stokes waves later. So moreover, from the work of Stokes, we know that the Stokes waves can be expanded into a series of the wave amplitude A. Here we have expansion for eta, for psi, and also for the speed c. Moreover, there's some very simple transfer variables that allow one to normalize the gravity constant to be 1. And that's what will be taken in the rest of this talk. Okay. So we have the reverse existence of Stokes waves as well as their expansions in terms of the wave amplitude A. So next, I'm going to talk about linearization and what we mean by spectral modulational instability. So we fix a Stokes wave, eta star, psi star, c star, and without loss of generality, let me take the air pressure for this Stokes wave to be 0. It can be any fixed constant. And notation-wise, I'm going to put stars everywhere for the Stokes wave. And let's say this Stokes wave has amplitude A is equal to some small number epsilon. Doesn't have to be positive, but small. So our goal is to investigate the modulational instability of this Stokes wave, right? And precisely the meaning of this instability is instability with respect to long wave perturbations of eta star and psi star. Right? That is, if we take the perturbations eta bar and psi bar, right? So the bar is for a perturbation, to have period L, which is much larger than the 2 pi, right? The period of the Stokes waves. So let me recall here the Zakharov Craig-Sulem formulation for gravity water wave in the moving frame with speed c. Okay. Now we want to linearize this system about this given Stokes wave. So we see that all the terms are easy to linearize because almost all of them are not local, except for this Dirichlet to Neumann operator, which is linear with respect to psi, but is completely nonlinear and non-local with respect to the surface eta. So we linearize it with respect to eta using the so-called shape derivative. It's given by the formula 9, which tells you how to take derivative of g eta star psi star with respect to eta star when acting on the perturbations eta bar. It is given by this explicit formula that involve, of course, the Stokes waves and the perturbations, where the functions b star and v star are computed explicitly in terms of Stokes wave by 10. So the meaning of b star and v star are exactly the vertical and the horizontal component of the velocity of the fluid for the Stokes wave restricted to the surface. Okay. Now with the aid of this shape derivative, we can linearize the whole system, and after some algebra, we end up with this system. We need some algebra in order to make appear these special combinations, the red combinations. Psi bar, the perturbation of psi minus b star, this function is computed in terms of the Stokes waves times eta bar, the perturbations of eta. So this leads to the introductions of the good unknown due to Alinek, where we say we introduce V1 to be eta bar and V2 is exactly these special combinations. Now with this new good unknown, we obtain the equivalent linearized system 12 and 13. So let me point out that the use of good unknown in the theory of world waves has been used in many works. In particular, the work on local wave positiveness, on nonlinear instability of solitary waves. And this explains why the formulations and the way we linearize the system about the Stokes waves are compatible with nonlinear estimate for the problem. So we see that in this equivalent linearized systems, all the terms are local. Right? Again, the star guy are related to the Stokes wave, and this is linear system for V1 and V2. So the only complicated terms is this Dirichlet to Neumann associated to the Stokes waves eta star acting on V2. It turns out that for the proof of modulational instability, we need to do a lot of exact expansions instead of estimates. So in order to deal with this term, what we do is we flatten the free surface using a Riemann mapping Z. The real part that we call Z1 and the imaginary part is Z2. So what it does is it maps the lower half plane, the flat lower half plane to the fluid domain of infinite depth, and in such a way that it respects certain periodicity and parity property of Z1, Z2, which again comes from the fact that the interface eta is even and 2 pi periodic. Now with this Riemann mapping Z equal to Z1 plus IZ2, let me define this Riemann stretch. It's a function of x only. It's a function on the real line, and zeta of x is Z1 at x0. So this is the image of the flat boundary under the real component Z1 of the Riemann mapping. And we denote the pull back by zeta sharp. Zeta sharp of f is f composed of zeta. Now we make a new change of variables using this Riemann stretch that we call W1 and W2. Then we end up with another equivalent linearized system for W1 and W2. Right? So this is a linear system for W1 and W2 with variable coefficients P of x and beta of x. So D variable coefficients are explicitly defined in terms of the Stokes wave and the Riemann stretch. Of course, the Riemann stretch, again, depends only on eta star. Moreover, with some work, we can expand these variable coefficients in terms of the amplitude epsilon of the Stokes waves like this. And the proof of the expansion make use of the shape derivative again. So now let's make it more precise what we mean by long wave perturbations. Right? So for long wave perturbations, we seek solutions of this linearized system WJs under the form e to the lambda t is going to be the growth rate in time times e to the I mu x times uj of x, where UJs are 2 pi periodics. Right? This has the same period as the period of the Stokes wave, and mu is a very small rational number. So mu is m0 over n0, m0 and n0 are integers, so that this perturbation WJ is L periodic, with L equals to n0 times 2 pi, and therefore it is much larger than 2 pi if mu is sufficiently small. Right? This is exactly the meaning of long wave perturbations. So now this leads us to the following eigenvalue problem: lambda of u equals to L mu epsilon of u. So u is the eigenvectors, lambda is the eigenvalue, and this operator L is given explicitly by this. So compared to the operators that we saw for the system W1 or W2, we see the appearance of mu in 3 entries. And the fact that we use the subscript epsilon here is to indicate the variable coefficient P of x and beta of x depend upon epsilon. So this is our main object. This operator is bounded from H1 to L2 on the torus, so the torus is for 2 pi periodic functions. So now we can make a definitions of modulational instability. So if there exists a small rational number mu such that this operator L mu epsilon has an eigenvalue with positive real part, we say that the Stokes waves is modulational, unstable. Okay. So now we can state the main theorem. So this is shown work with Walter Strauss. We prove that there exists a positive small number epsilon 0 such that for all Stokes waves with amplitude smaller than epsilon 0, there exists a small number mu that depends upon epsilon, such that whenever you take mu non-zero and smaller than mu 0 in absolute value, then the operator L mu epsilon is an eigenvalue lambda with positive real part. Moreover, we have the following asymptotic expansion for lambda. So to leading order, the imaginary part of the eigenvalue is a half mu, and the real part is 1/2 square root 2 absolute value of mu epsilon. Right? So this real part is positive because both mu and epsilon are non-zero. Right? So you wouldn't see this instability if either mu or epsilon is 0. Okay. So if we view this unstable eigenvalues is a curve of the parameter mu, then we see that the slope of this curve is proportional to the inverse of the Stokes wave amplitude epsilon. In particular, it is very large for small amplitude Stokes wave. And this qualitatively agreed, at least, with a numerical results of the Koenig and Oliveras in 2011, where they numerically computed the spectrum of the linearized operator. And so this curve is the spectrum. It consists of eigenvalues of the linearized operator. This is clearly a figure 8, right? And if we look at the scales of the axis, we see that the scales of the real axis is about 1% of the imaginary axis. That means close to the origin here, the slope of this curve is very large. And that is how we prove it here, right? So we justify these pictures, at least near the origin here. So this is the main result of the talk. And in the rest of this talk, I'll try to outline some main idea without going to detailed proofs of this result. So again, let me recall this operator that we after. Now, the operator has two parameters, mu and epsilon. It turns out that there is only one order of perturbations that, sorry.
There question from Masi.
Okay.
What is the shape of the corresponding eigenfunction which is unstable? So what is the direction of instability?
I'm sorry, what is the direction?
Of instability. So the eigenfunction which corresponds to these unstable eigenvalues, what it is?
Okay, so you will see that in the talk because we really construct some expansions of the eigenfunctions. Okay, when I outline the proof of the talk. Is that answer your question?
Okay, we shall see. Yes, thank you.
Okay, so after this operator, which has two parameters, and it turns out that there's only one way of perturbation that leads to the instability. I mean, that gives the proof of instability, which is you have to first perturb epsilon first and then mu, right? Just as stated in our main theorem. And this operator, the study of the spectrum of this operator is quite difficult because it has variable coefficients, p of x and beta of x. So let's first take epsilon equal to 0, in which case these variable coefficients become constant, and this operator can you can find the spectrum of this operator by Fourier series. So it has a discrete spectrum, a lambda given by this formula. They are all imaginary. Right? They are known by I omega k mu because it depends on the Fourier variable k and the mu, right? The parameter mu. So you see that for small parameter mu, for all small parameter mu, the spectrum is separated into two parts. This is the red part and its complement. The red part is the part that is close to the origins, and the complement has a distance of order 1 away from the origins. So these four eigenvalues correspond to the choice of k equal to 1, 0, I'm sorry, to 0, or when you take k equal to 1 and you take the minus sign, right? So that this becomes mu minus square root of mu, which is small for mu small, or you take k equal to -1, but you take the plus side here. Okay. So you have four of them close to the origins when epsilon is 0 and mu small. Now, if you further take mu equal to 0, then these four eigenvalues collide at the origin. So the conclusion is that for the operator L00, when both parameters are 0, the eigen 0 is an eigenvalue with algebraic multiplicity 4, and this is the only one in the neighborhood of the origin. Okay, so next we want to perturb epsilon, right? This is the correct order of perturbations that we want to do. Epsilon first. On one hand, by standard perturbation theories from the book of Cairo, the spectrum of this operator, right, mu equal to 0, we perturb epsilon, is also separated into two parts, where the part near the origin must have total algebraic multiplicity 4, because we have that when epsilon equal to 0. Now, we prove that the first theorem in the proof actually is to prove that these four eigenvalues again collide at the origin. Exactly is for the case that epsilon equal to 0. Okay, so we prove that for sufficiently small epsilon, 0 is an eigenvalue of L0 epsilon with algebraic multiplicity 4 and geometric multiplicity 2. Okay, and we give explicit formulas for these eigenvalues eigenvectors and generalized eigenvectors. So we have two eigenvectors and two generalized eigenvectors. So even though I'm not giving the proof of this result, let me briefly mention that the eigenvectors come from invariances of the system, and the generalized eigenvectors come from the fact that the family of Stokes waves depends upon two parameters, the wave amplitude A and the air pressure P. Okay, and I didn't know the second eigenvectors by U tutor for some reason that you see now. Okay, here I have some relations between the generalized eigenvector and the actual eigenvector. And we want to normalize the second eigenvector U2 tilde to U2 this way so that it has mean 0 and to leading order. It doesn't depend on epsilon. Okay. Now from this explicit formula for the generalized kernel of L0 epsilon, and from the expansions that we have for the Riemann stretch theta and for the Stokes waves, eta star, psi star. With some calculations, we can get the expansions for all the eigenvectors, U1 up to U4. Okay, so they are series in epsilon and depend only on epsilon. So even though I'm not mentioning detail the proof, it turns out important in our proof that we need not only the detailed expansions of these eigenvectors, we also need a certain period of them. So for example, here U1 and U2 are odd even in the two components, because the first component is for 8R, the second component is for psi, while U3 and U4 are even and odd functions. Okay, so this, so we just show that when we fix mu equal to 0 and we perturb epsilon a little bit, in the neighborhood of the origin itself is the only eigenvalue with multiplicity 4, the algebraic multiplicity. So the next step is to perturb mu, right? And we do this by a Leopold-Schmidt method. Again, we after this eigenvalue problem for L mu epsilon. So let me denote by script U the generalized kernel we just found, which is 4-dimensional, and pi is the orthogonal projection onto the orthogonal complement of U with respect to the L2 inner product. So pi is the projection onto an infinite dimensional subspace of L2, which has codimension 4. And with these introductions of these projections, the eigenvalue problem that we after now becomes a system of two equations, where the first equation is infinite dimensional because this is projected by pi. The second equation is 4-dimensional. Okay, so what we do is, by this Leopold-Schmidt method, we first solve the infinite dimensional equations and plug the solution into the finite dimensional equation to end up with some algebraic equations for some coefficients that we will see now. Okay, so any solution U is eigenfunctions must be written as linear combinations of alpha j uj's and a function w that is orthogonal to all the eigenvectors uj. Right? It's general. Now, by linearity with respect to the coefficient alpha j, the w, the function, must be a linear combinations of alpha j and some vector wj's. And we call these guys sideband functions because they come from perturbations in mu. They wouldn't be there if mu is 0. So wj solve this equation 26. Right? It's projections, this operator acting on the sum of uj's, which is none, plus wj is 0. We want to solve this for wj. And the way we solve this, okay, we have to make the connections between this projection pi and this operator. So remember that pi comes from the kernel of L0 epsilon. That's why we want to decompose now this operator into L0 epsilon and the perturbations. Right? It turns out that the perturbations has this form. This is proportional to mu times a new operator which is independent of mu but dependent on epsilon, and I call it L epsilon dagger. Now, with these decompositions, the equation that we want to solve for the sideband function wj's become these equations. The right-hand side is given because it depends only on uj. We want to solve this for w. So what we do is we invert this operator, the red operator pi L0 epsilon. In order to do so, we prove another theorem that for sufficiently small amplitude epsilon, this operator is an operator from H1 to L2 is a Fredholm operator with the kernel U and the range U part. Okay. The statement about the kernel can be proved relatively easy, but the statement about the range is non-trivial because you see already the range of pi is U part. So it tells you that if you pre-compose with L, you don't lose anything when you take projection. So with this theorem, we can invert the rest operator pi L0 epsilon, and let's denote by C epsilon, the inverse. It's just appear locally here, and I won't mention about it again. So now we can solve this equation by inverting this, and we assume that both mu and lambda are small, so that we can use Neumann series to solve this equation for wj. This is given by this Neumann series that depends only on C epsilon, L epsilon, L dagger epsilon, and the eigenvectors uj. So we like to stress that unlike the simplified model for water wave, the sideband functions Wj contribute crucially to the proof of modulational instability. Because in the proof of theory, so for models of water wave, usually there are negligible errors. Okay. So now we have, remember that we are solving the infinite dimensional equations, and the solution is of this form, where W is further decomposed into these linear combinations, and we just found a solution for W. So what we do now is we plug this form into the second equation, the finite dimensional equations, and we get a 4x4 system for the coefficient alpha j, which has a non-trivial solutions if and only if certain determinants is degenerate. And this is determinant of these sums of the three matrices, where the matrix A and I are defined this way. So they depend only on the operator L mu epsilon and the eigenvector Uj. But the matrix B, the red one, depends also on the sideband function Wj. And that's why we call them the sideband matrix, B mu epsilon. And for the proof of modulational instability for the full water wave model, one of the difficulty comes from the fact that we have to study in details this matrix B and its interactions with the blue matrices. So in summary, after performing this Lipponet-Schmidt procedure, what we have shown is that the Stokes waves is modulationally unstable if there exists a small rational number mu such that this characteristic equations has sufficiently small root lambda with positive real part. Okay, so now our goal is to study this determinant, and what we do is we expand it with respect to two parameters mu and epsilon. So we first study the easier part, the blue part, which is the sum of A mu epsilon minus lambda I epsilon, because remember that these matrices are defined in terms of these non-objects. Okay, so after very long calculation with a lot of expansions, we get the following expansions for the blue part. Okay, so if we denote by pi 3 mu lambda, this kind of homogeneous polynomial of mu and lambda. So notice that it doesn't have the terms lambda cube. Okay, that expansion of this determinant is this blue term, okay, which has this double root. Lambda equal to a half I mu will be our double root. And in the second line, we have higher order terms for epsilon, and the special thing is that, again, this double root appears here with power 2 and here with power 1. And the last slide is an error. And for us, it is an error whenever we have small enough amplitude, which is epsilon cube, or we have high enough powers of mu and lambda, specifically to the power 4. Okay, so we got this after very long calculations and expansions for these matrices. And the next step is the contribution of the sideband matrix. So what we mean by this is we look at the difference between the whole determinant and the determinants of the blue term, right? It tells you what's the contributions of this red sideband matrix. And again, this is a very long and detailed expansions. We get the following. So the leading term for us in the red term is minus 1/8 mu cube epsilon squared. In the second line, we again see the appearance of that double root we just saw in the previous slide. And the last slide is the same kind of error terms, good error terms. So for the proof of this, we not only need to look at the detailed expansion of each entry of this 4x4 matrix, but we also need to how it interacts with the blue matrices. Okay. In particular, recall that the matrix B is defined upon Wj's, the sideband function, which is given by this Riemann series. And this makes the detailed expansions be complicated because this formula involves the inverse C epsilon, which is implicit. Okay, but I will not give detail of this long expansions. Now, if we summarize these two propositions, we get a full expansions for the characteristic functions. that we want to solve for lambda. It's P lambda with the two parameters mu and epsilon is given by this. This is double root. Our double root will be a half I mu. And this very important red term which come from the sideband matrix. And it will be crucial for us that the red terms here come with a negative side. Because of the negative side, we will get a real part of the eigenvalue lambda. So now we want to solve this expansion equals to 0 for lambda. Of course, the solution to lambda, the eigenvalue lambda will be depending on the parameter mu and epsilon. Okay, so the way we solve this again by the perturbations in the correct order. We will perturb in epsilon first and then in mu. Okay, but before we do that, we have to rescale these equations. So we see that the first and the second line, so let's neglect the root remainder. The first two line, it is a cubic polynomial with respect to mu and lambda, right? So that's why if we change the variable, we rescale the eigenvalue lambda to be mu times the mu variable gamma, then we can factor out a mu cube in the characteristic function p. And we get the new function that we call p tilde is now a function of gamma with two parameters mu and epsilon again. It's this explicit form. So again, the blue terms come from the blue matrices, and this come from the sideband matrix. Now our observations, another observation is that this first error terms, remember we always have two error terms, this is the first one, it depends only on gamma, independent of mu. So this is also true for the first line, right? So if we call the first line plus the first error term q tilde is something independent of mu, but depend only on epsilon. And the last remainder is a function of all variables, right? Now, it is because this guy q tilde is independent of mu, we can do a perturbations in epsilon. Okay. And because of the, so let me also mention that because of the pi 3 that we had before, this function theta 1 is actually a quadratic functions of gamma. So we see that we want to solve this q part for gamma. And again, because as I mentioned earlier, because of this negative 1/8, we get two symbol roots that are denoted by gamma plus and minus, depending on the parameter epsilon. The imaginary part is the double root, is 1/2 I, and the real part is proportional to mu times another functions of, sorry, is proportional to epsilon times some other functions that I call kappa of plus or minus epsilon. And when epsilon equals to 0, this function takes the real value plus or minus 1/2 square root of 2, which is precisely the square root of this measurable number 1/8. Right? So we have solved this part. So we neglect the last remainder term and solve this part by perturbations in epsilon. And next, we can perturb in mu, right? Because the p tilde is just the q tilde we just solved plus perturbations in mu. When mu is equal to 0, we just solve it. We got two simple roots. Therefore, by means of the implicit function theorems, these sums must have at least two simple roots. But now it depends also on mu, provided that mu is small enough, and the smallness depends upon epsilon, right? So we arrive at the final theorem. So for all epsilon small enough, smaller than epsilon 0 that we just fixed in the previous slide, and for all mu small enough, smaller than some mu 0 epsilon depending on epsilon, the characteristic functions p has at least two simple roots, right? Simple roots, and we got this by multiplying the roots of p tilde by mu, by recalling the rescaling that we said in the beginning, lambda equal to mu gamma. So to leading order, the imaginary part of this eigenvalue is 1/2 mu, and the real part is plus or minus 1/2 square root of 2 mu epsilon. And because at least one of these two eigenvalues must have positive real part, right? We conclude the instability, the modulational instability of Stokes wave with small amplitude in deep water. And this leads to the end of my talk. Thank you for your attention.